Here's an argument for the fundamental theorem of calculus. I'll be putting together the idea of the definite integral with the idea of antiderivative. Okay, so suppose we have a velocity function that is the derivative of a position function, and suppose that the position at time 1 is x1 and the position at time 2 is x2. Then we can rearrange this derivative into the form dx equals v dt. And then what I'd like to do is sum up a whole bunch of these infinitesimal displacements to find a finite displacement delta x. So add up a whole bunch of little changes on this side and on this side. So we write our integration symbol on both sides, showing that we're going to add up an infinite number of infinitely small things. So here on this side, we're adding up an infinite number of these infinitely small areas as expressed as the height of a thin rectangle times the width of a thin rectangle. Let's look at the limits of integration here. Note that on this side, the left-hand side, our independent variable is x. On the right-hand side, our independent variable is t. So our limits, our lower and upper limits of integration should refer to the independent variable. So as time goes from time 1 to time 2, x is going to be going from its initial value, x1, to its final value, x2. So it's important that the lower limits sort of agree in the sense that when this independent variable t has value t1, at that moment, this independent variable x has value x1. And when t has value t2, x has value x2. So these sort of match, our lower limits match, and our upper limits match. So here we've got our definite integral. Okay, on the right-hand side, we know when we add up all of the little dx's, we'll get the big delta x. And delta x we know is the change in x, so x final minus x initial, so x at t2 minus x at t1. Carrying down the definite integral on the right-hand side, we get to here. Okay, next step. If x is the antiderivative of v, and we know it is because our velocity is the derivative of position, so position would be the antiderivative of velocity. Then this equation here is saying that the antiderivative of the velocity at time 2 minus the antiderivative of the velocity at time 1 is equal to the result of our definite integral. So I've written exactly that here. The antiderivative of the velocity, and we should say with respect to the independent variable, t, the antiderivative of the velocity at time 2, that's this here, x at time 2, minus the antiderivative of the velocity at time 1, that's this, x at time 1, is equal to the result of the definite integral. This, in brackets here, is basically the statement of the fundamental theorem of calculus. This is how to integrate, meaning evaluate the definite integral. We can get the result of the integral, the area under the curve, if we can find the antiderivative of the integrand here, evaluate that antiderivative at the final time, evaluate the antiderivative at the initial time, and take this value minus that value. That will give us the area under the curve, the result of our definite integral. Writing antiderivative at time 2 minus antiderivative at time 1 is cumbersome, so we do have a shorthand notation here. I'm just going to switch the two sides here, flip those, and move the definite integral over to the left-hand side. So here we have just rewritten the integral of v dt from time 1 to time 2. So this represents the area under that velocity curve between times 1 and time 2. That's equal to, and here's our bracket notation. We say the antiderivative of the velocity with respect to the independent variable, t, time there. The antiderivative of velocity, when we put this in brackets and write the lower limit here in the lower right-hand corner of our bracket and the upper limit here in the upper right-hand corner of the bracket, what this means is take the thing in brackets, evaluate it at time 2, the upper limit, and then do minus the thing inside the brackets evaluated at time 1. So rather than writing this twice here, we write it once, put it in brackets, and say we'll evaluate it at time 2, then evaluate it at time 1, and take the difference. So here, once more, we have the fundamental theorem of calculus, or expressed this way, it's often called the second fundamental theorem of calculus, but that distinction won't be important to us. This was all in terms specifically of position and velocity, but we can write it in a more general form. If we have some function f that's a function of some independent variable x, so instead of time t, we're replacing t with some generic variable x. So if f is a function of x, and we want to find the area underneath this f function between some value x1 and some value x2, then that definite integral has the result of this definite integral, the area, can be found by determining the antiderivative of that function f with respect to the independent variable x. And in brackets here, this means we're going to evaluate that antiderivative at the final value of x, and then subtract from that the value of this antiderivative evaluated at the initial value of x.